Hey, thank you, everybody. My name is Jeremy. As Gautam mentioned, I'm a PhD student in statistics at Penn State University. And what I'd like to talk about today is how statistical methodology at a high level can help us think about bridging this gap between theory and practice that we think about a lot when we take these nice properties of differentially private systems and we try to implement them in the real world. And there are two forms of slippage that I think are really interesting, and there's a lot of nice work that we can start to think about. On the privacy side, we want to think about adversarial modeling when the adversary's information changes based on the information of how that system is implemented. And we also want to think about how the way in which we conceptualize utility changes when we start to additionally think about how we can quantify uncertainty. And I've broken this talk into sort of four separate parts. The first part is I want to talk about this problem at a high level, thinking about all the different ways in which we can motivate this kind of research and why it's really important that we address it. Thinking then about, in the second part, the implications specific to privacy, the third part specific to utility, and then at the end, sort of a wrap up and discussion of how we can think about these problems, not only during this talk, but throughout the workshop. So the reason we're all here is because differential privacy has really good theoretical guarantees. We know that because of the verifiable nature of the way in which we develop differentially private mechanisms, that we have some degree of agnosticism to different adversarial models. We also know that because the form of the mechanisms themselves can be disclosed transparently, that we can design mechanisms in a way that meet particular optimality guarantees and particular reproducible inferences, namely that we can adjust, theoretically at least, for the kinds of errors that we're introducing due to privacy. Now, all of this is contingent on a deeper set of assumptions. And whether or not these assumptions hold when we actually build these systems becomes a bit of a problem, because unlike in the sort of theory world where we're just developing a particular mechanism in this like nice black box, whether or not we've met the assumptions necessary when we build one of these systems in practice can be more of a gray area, where it's less binary whether or not a system has these properties or not. In particular, for privacy, we care about the situation when there could potentially be dependencies on the confidential data based on the way in which we're actually implementing the system. And for utility, we care about, at a high level, what could potentially happen when the kinds of optimality that we care about for a particular mechanism don't necessarily translate to the kinds of utility that maybe are not strictly based on distance to a particular optimal estimated result. Maybe it's based on our ability to quantify that uncertainty. And there are lots of different needs in that all along the statistical spectrum. Now, all this is very abstract, so I'd like to kind of concretize this with to show one example where a lot of these problems are things that we might typically abstract away when we're doing research. So suppose we have some data curator who wants to release statistics about patients affected by COVID-19. This is an area of research where there's lots of active work and there's lots of privacy concerns. And typically, the unit of analysis that we think of when it comes to how we're framing our research is based on the mechanism forward. But there's lots of problems in terms of where the slippage between theory and practice occurs. Namely, this data is not something that is created and then hermetically sealed until we decide to use differential privacy. Oftentimes, this data is used in lots of different contexts, both internally and externally. We also need to recognize that just because a differentially private algorithm is existing for these statistics, it doesn't necessarily guarantee that realistic reconstruction attacks are infeasible. This matters in particular for health data because at a high level, we could think about health data being released at particular points in time. And if those time points are correlated, then we might not have those same DP guarantees in practice. And if there are particular kinds of linkage attacks that we might want to protect against for health data, then it's unclear if simply saying we're using DP is going to be good enough. On the utility side, there are problems that we have with these more operational constraints in terms of the way in which we release the data, how we choose which analysts and what queries we're going to answer, and how we address certain uncertainty quantification needs. It's one thing to say that we could guarantee that two results are close together, but in the context, say like for this COVID-19 data, there might be particular models that privileged people might need to run. For example, let's say a health organization needs to run a risk analysis model for emergency planning for COVID-19. They might have analyses that have a dedicated budget, But for more public use data, say like someone in a local area trying to figure out if that disease is affecting them, that's something where they might be forced to work with this indirect result, working with microdata or something that doesn't specifically tailor to their analysis goal. There could also be operational constraints in terms of how the data is created, in terms of meeting a particular format, such as being published as microdata. All of these things are things that we assume typically are solved problems by the time we get to coming up with a mechanism. And there's the statistical perspective is something that I'm going to argue today allows us to think about how these should inform the way that we design mechanisms. And in the second part of the presentation, I'm going to talk about this from a utility perspective, thinking about these first two kinds of problems that arise. And in the third part of the talk, I'm going to talk about these sorry, I misspoke. This first part of the talk is going to be the privacy-specific side, where I'll talk about how public information affects these adversaries. And in the third part of the talk, I will discuss the utility implications for all of this. So why this is really, really important to talk about, and why I think there's a lot of fertile ground for research here, is that the consequences of misspecifying like the way we think about theory and practice are almost always in the direction that we don't want. When we think about these forms of slippage, it's usually we're underestimating the adversarial information that people can have, and we're overestimating the sort of practical utility of these releases for particular tasks. And a lot of this slippage comes from the fact that the way these systems are developed is not you are handed a set of parameters and this is what we're going to do. Like going back to our health example, if you are the organization running this, you're not going to magically say, answer these queries with this budget. There's going to be an iterative process, and that process is going to be contextually specific to the data generating process. And it also is going to depend on the history of that database, whether or not differential privacy was part of it or not. And this is something that's important for not only the people in this room, but how we talk about differential privacy to a wider audience. Because we tend to think about this in these sort of monolithic binaries. Either a system is private or not private. Either a system like has optimal utility or suboptimal utility. But when these assumptions enter the picture and we don't know for sure the degree to which they've held, we can't necessarily communicate in these binaries. They're multidimensional problems, and statistics gives us a perspective on how we can think about them more holistically. So the way that we're going to think about this now, taking those ideas sort of abstractly and making them more mathematically consistent, what I'm going to do is we're going to think about a world in which we have some parameter of interest that we're trying to do inference on. We have our confidential database X, and we're going to assume some class of models that could generate this confidential data, and we're going to assume a particular mechanism, M of X, which is going to generate our randomized output Y. And in this model, there are sort of two different kinds of information updates that are happening. On the left, we have the adversary who is trying to use this sanitized result to update what they might want to learn about the confidential data X. And on the right, what we're doing is we're trying to take this private result, account for the fact that we've introduced this mechanism MX, and use it to do inference on theta. And because of the impossibility theorems and what we've formalized about differential privacy, we're trying to make the person's job on the left as hard as possible, while making the person's job on the right as easy as possible. And this is based on thinking about two different steps in this directed acyclic graph, where we're trying to prevent inference one step up the tree while making inference as easy as possible 2 steps up the tree. Now, where this breaks down is that when we have some information that is coming outside, that is correlated to the confidential database and informs the way in which we are actually creating this mechanism, then the semantic guarantees that we typically associate with differential privacy, this sort of prior to posterior or comparison of posterior's approximation, this isn't going to work. And we're going to refer to this in this case as this random variable Z as our public information. And this is what the original sort of theoretical motivation is for why, when we build these systems, ideally everything should go through this mechanism so we don't have these sorts of side channels. And this is what we ideally want to ensure. we want to make sure that this Z doesn't exist. And one of the unfortunate things is doing that is very, very difficult and in many cases near impossible, simply because there are too many different societal forces that make setting up these systems in a way that is entirely data independent, like very, very difficult or entirely infeasible. Namely, at the time that you're implementing these systems, there are so many different laws, norms, and ways that are contextually established as to how we generate data and how we share data or information about this decision-making process that make this really impossible. We also have this problem where when the data is used in multiple places beyond that, we don't necessarily know what the relationship is between these past releases and the current releases, because databases are not these static objects. They are things that evolve over time. The contributions evolve over time. And there are countless examples of this in sort of like the applied privacy literature that talk about all the different ways in which this public information can either be accounted for in these different models or can start to break down the certain kinds of structure that we care about. So this is, even though we might tend to think of this in sort of like the strict mandated sense, it really is something that shows up pretty endemically in these sorts of problems. So the way that we're going to think about this is the way that people in statistical disclosure limitation have thought about this for far longer than the existence of differential privacy, which is that we want to think about what kinds of adversarial model assumptions we're making. And what I'd like to do is talk about how we can formalize this in a way that is compatible with the semantics of differential privacy. So for us to do that, we need to think about how our public information Z informs the spaces of all possible models on our confidential data X. And then when we see one realization of our public information Z, this is going to give us a class of conditional distributions where we want to have these same semantic guarantees. And we're going to interpret this as a collection of pufferfish privacy mechanisms, for those of you who are familiar with this. And our goal is to be able to distinguish between events, which we'll call secret pairs, these S1 and S2. An example of this might be if you want to protect whether or not a particular person in the data set has COVID-19 positive or negative. And what we're going to do is we're going to restrict this set to only those for which the public information doesn't tell us something deterministic about which one of these events is true. And this is necessary because whenever we are introducing this public information Z, we are going to be taking our uniform guarantees from epsilon dp and reducing the space over all these comparisons for which these actually hold. But for this set, we have this interpretation that is instead based on these conditional distributions here. So we have the same distance between these probability distributions as epsilon dp, but it is now based on the conditional distributions, including this additional information coming from Z. And to sort of visually illustrate the point that I was making earlier, this is necessarily a relaxation because of the public information problem that we have. The way that we typically think about differential privacy is these guarantees are holding over an entire schema, or the set of all possible databases that could be generated under a particular way of defining a particular record. And this has sort of been the unit of analysis for formal privacy for a while. And this is very different from the way that traditional statistical disclosure limitation has worked, where you're describing one particular database and your guarantees only hold for all such databases that have that same value. So the equivalence class induced by that. And what we're doing is making an assumption that was always there more explicit, so that we can explicitly interpolate between these different kinds of units of analyses, where we want some guarantees over some subset of the partial schema, knowing that we can't get them necessarily over the whole schema by construction. So the nice thing, though, is when we formalize it as this, we can maintain the same properties that we would normally get with epsilon dp. In particular, we still have sequential and parallel composition. We can do post-processing now, not only just with the sanitized result Y, but we could also post-process as functions of the public data Z. So this is something that is very helpful, but the question is, where on this spectrum do we want to lie? And that's a question that becomes a modeling problem. It's a question where we need to think about how big do we want to allow this space of potential dependencies to be, because we don't want it to be too big or too small because of the sort of bounds on the way that we've set up this problem. So if we assume a best case scenario where this public information is entirely like detached from our confidential data, then we're in a situation where we have the same epsilon DP style guarantees, but that translation into the semantic interpretations that we care about is going to be limited. At the same time, though, we can't just allow for arbitrary dependence, because then we won't be able to maintain any reasonable utility. And this is just a way of restating the no free lunch theorem. So what we need to do is think about how we specify this class of models. And one of the nice things is, because of the way we can interpret this, we can interpret the loss that's incurred if we specify a particular class of models, and the process that actually generates the data is something that comes outside of this space. Namely that if we're doing this, we're going to incur an additional privacy cost due to this misspecification. So there is a little bit of hope, depending on whether or not we potentially make our class of capital theta Z too conservative. And it's based on this form that we have right here, which is based on a similar log-max divergence between our misspecified data and the conditional distributions induced on these two secrets. So next we need to think about how the mechanisms that we normally use are going to operate in this situation. And when we're working within a situation where we're no longer looking at individual databases but on distributions, we have to think about distance a little bit differently, because we're no longer considering distances based strictly on 2 points in a particular metric space. We're now considering distances based on distributions. So for us to have an analog of sensitivity, what we need is a way of measuring how much, conditioned on these two individual secrets, these probability distributions change. And the worst case among the class of models that we specify is this capital delta Z that we have here. Then for that capital delta Z, we can define a sensitivity for any individual function as the most that function could change given two databases that differ in the metric space based on this movement in probability mass. So it's the sort of two-stage sensitivity calculation. And once we have this, we have the same way of using mechanisms that we would previously use, except it's now based on the solution to this optimal transport problem. And the reason I bring up the exponential mechanism in this primitive in particular is because there are two things that this mechanism allows us to do. So at a high level, it allows us to solve an optimization problem while satisfying this relaxed version of differential privacy. At the same time, though, there are two nice aspects of this that we can think about. One is that the base measure for which we implement this mechanism can itself depend on the public data. And this is something that is a really desirable property because it allows us to think more holistically about these dependencies between the public and the private data. We often care a lot about congeniality, making sure that we release a result that agrees with some public statistic. We also might want to use that public information to inform a base measure that maybe is data dependent, that's maybe based on prior information. This is something that's really important when there's spatial or temporal autocorrelation in data. There's also, we can get additional results that improve the utility of this mechanism when, instead of looking at generic measure spaces, we look at those which have some sort of metric structure to them. In this case, we have a variant of the k-norm gradient mechanism called the Wasserstein k-norm gradient mechanism, which will guarantee central limit style theorem asymptotics for this particular mechanism. So in order to keep us moving along, I'm going to move away from the sort of first two parts of the talk towards the rest of the talk, where we're thinking not as much about the privacy semantics, but more about the utility within the same sort of perspective. So the way that we typically think about this problem when it comes to designing an optimal estimator is we have a situation where we are trying to, among some class of estimators, this capital theta, and among some class of privacy preserving mechanisms, this script M, we're trying to minimize some way of representing this loss function L as a function of the way the data is generated. And we have two sources of uncertainty that we have to consider. One is the uncertainty coming from our data generating process, and one that is coming from the way in which we define the actual mechanism itself. And the way that we consider this is through the marginal, this lowercase m, where we're actually integrating out the effect of the confidential data. And the way that we typically think about this in differential privacy is we consider the script m as the set of all mechanisms that satisfy a particular budget constraint and that run into particular complexity for actually generating that sample. So this is the typical apples to apples comparison that we see when we're in this sort of space comparing different mechanisms. Now, this is a problem that has showed up in a lot of different places, not just DP, but also SDL. We have a review paper where we go through the number of different examples talking about this. And what I want to focus on today is cases where the space of mechanisms M doesn't necessarily consider other sort of sociologically important dimensions where not every element in the space of M is going to satisfy utility needs, not strictly those specific to the particular problem at hand. And I want to talk about these sort of two forms of slippage. One is that different mechanisms are going to accommodate different kinds of either analytic or computational kinds of uncertainty quantification. In a best case scenario, we can think about a particular model and a particular statistic that we want to release, and this mechanism giving us an analytically tractable form for the way in which that statistic is related to this analytically known form of error. This is our best case scenario. The worst case scenario, which is unfortunately sometimes true, is it could be potentially computationally or analytically burdensome to generate even one sample from this mechanism. And these are problems with scale, this is a problem with operational constraints, but these are two ends of a spectrum and mechanisms can be anywhere in between them. We similarly have problems with the size of the space and what is operationally available to a particular data user. Lots of data users are not going to have the ability to specify a mechanism specific to their analysis task, which is sort of our best case scenario, where we might often be in this worst case scenario, thinking back to our sort of hypothetical example, someone who is reconstructing a local health statistic based on aggregate statistics published at a different organization, where that mechanism might be fixed in advance and they're only ever optimizing over that theta itself. And to address this first collection of points, we have to think about what it actually means to do this correction. And measurement error methodology is a relatively old field in statistics. It's been around for maybe 50, 60 years. And there's sort of two general schools of thought in how we can actually work on these kinds of problems. That we can think of the statistic that we would ideally use in a non-private setting, this T of X, as either something that we're considering missing or something that we're considering latent. So instead of doing inference on theta given T of X, we're doing inference on theta giving our private result. And there's sort of two different ways of approaching this. In the missing data approach, we can either analytically think about a appropriate substitution for this statistic under this particular model, or we could think about a method to allow us to numerically impute different versions of this under some computational constraints. If we want to ignore any sort of method that works directly with this T of X, then there are resampling approaches, semi-parametric models, and there's also lots of work in MCMC and approximate Bayesian computation that work on these problems. Now, these are things that there are whole textbooks written on this subject. I'm not going to attempt to summarize a bunch of textbooks. There will be some talk specific to differential privacy on this later on. What I want to focus on today is that different mechanisms are going to sit in different places on these two spectrums in terms of different analytic tasks in increasing complexity from only being able to describe the asymptotic behavior of this mechanism down to writing down the density. And then on the computational side, thinking about only being able to draw one approximate sample from this distribution all the way to being able to sample exactly from the posterior of interest. And anytime we move up even just one rung on either of these sides, we're going to run into like non-trivial problems in computation. One example of this is based on seeing the first two bullets on the computational task side, where we sample either from an approximate mechanism or from an exact mechanism. And what we have here is some experiments we did based on an exact sampler that we developed in a previous paper. So we're trying to implement an exponential mechanism constrained with L1 noise on a hypercube. The x-axis here, we have our privacy budgets increasing as x increases. And on the y-axis, we have the number of proportions that we have to randomly sample in order to implement this algorithm. So the runtime of this algorithm is itself random. And these violin plots are going to be wider when the density of each of these rows is larger. And we see that as the privacy budget increases, the number of samples that we need to draw additionally increases. So there's this third dimension to the problem privacy utility and computation time that further toggles the way that which we're trading off whether or not we want to be approximate or exact in how we're generating this sample. So these aren't just abstract problems in the first sense, they're also abstract problems in, these aren't just concrete problems in the first sense, they're concrete problems in the second sense. So most of the way that we operationalize the work that we do is by thinking about what kinds of outlets that people are going to have to be able to design mechanisms, work with someone to develop that particular result. But for the kinds of people who have to adjust for particular mechanisms, by construction, we know that the optimization is not going to be the same. If we're just picking any particular mechanism in advance and trying to correct for it, we know that the optimal estimator that we design for adjustment is not necessarily going to be the same estimator that we design if we can also itself vary the mechanism. And this shows up in a lot of different places, namely because when we change our loss function and when we change whether or not we have the freedom to construct the mechanism, we are running into different kinds of optimization solutions. So going back to that example that I was talking about earlier, if someone is working directly to create a risk analysis for COVID-19 data, and they have the ability to say, I need this exact statistic for this model, they will have a more optimal utility trade-off than someone who only has, say, aggregate statistics or microdata and has to make a smaller scale decision. And in particular, thinking only about the design perspective is going to potentially foreclose or make inferences in this adjustment setting weaker. And this is particularly important for the way that we think about post-processing, because when we have public information Z, it's tempting to want to combine the two via post-processing in order to get more optimal results. However, for certain kinds of inferential problems, we could be in a situation where not post-processing is going to save us some additional utility in this adjustment perspective. So in this paper that we have, we talk about how certain kinds of finite sample inferences can be more powerful, not only in expectation, but for exponential family models, a very wide class of statistical models, it's going to actually be a uniform dominance. And I'm running a little bit low on time, so I have a number of case studies in the appendix where we talk about how these effects are not only theoretical, but they show up in real analyses where post-processing is really going to degrade a lot of the way that we think about these inferences. So just to quickly summarize in the last couple of minutes I have, so this work talks about a way for us to sort of formalize in the language of differential privacy how this slippage between theory and practice occurs, and the way in which we can start to work through these ideas and sort of meet in the middle between these abstractions that we create for generating mechanisms and the kinds of issues that show up when we realize these systems and we try to build them in practice. And what I think is really important for us to focus on during this workshop is what it means to, when we design a mechanism, what are the additional steps that we need to take to make it operationalizable? In particular, if there are parameters that we need to set in advance or otherwise, is there a way to set them in a way that is optimal without inducing too much dependence on the data? And if so, what does that dependence look like? Additionally, we need to think about whether or not a particular mechanism omits a certain kind of uncertainty quantification representation and what it would mean to modify it if we were constraining the space of possible mechanisms to those that had different computational restraints on whether or not that was operationalizable or not. And at a high level, these are things that are not just abstract concerns. They have really concrete implications for the way we think about this, because there's lots of differential privacy is slowly becoming not just this theoretical tool, but something that's now being used as a legal mechanism, as something that's demonstrating compliance with privacy law. And if there's this difference between how we theorize about it and the way that it shows up in a real-life system, this is going to produce problems. And in terms of operational equity, knowing that data users are going to be diverse and we're not going to be able to satisfy everyone's needs means that we need to think about the kind of equity and burden issues that show up when not everyone has the technical or operational capability of thinking about these measurement error issues. The analyst working internal to the organization versus someone who's using the results of these outside of that, that's a disparity that we do need to think about when we're designing these systems. So I'm a little bit over time, so I'm just going to wrap up now. What I hope that we could take away from this is sort of a constructive perspective in terms of where our two fields, and again, it's a very, very loose boundary at this point, where I think the two general dominant perspectives in these fields can help each other. In general, computer science approaches are very good at abstracting away problems and thinking about optimization techniques to solve those. And what I think we could do is work towards taking some of these ideas and operationalizing them in terms of the constraints on the mechanisms that matter most for uncertainty quantification. And in the reverse, I think there is a lot of interesting learning theoretic work we could do in terms of thinking about how these constraints are going to manifest in terms of characterizing the space of mechanisms, either using the tools that we already have or geometric approaches, something like that. So here are the papers that I talked about, and that is the end of my time. Happy to take questions. Thank you.